Hello and welcome. Today we are going to talk about getting started with PyMol and VMD. We're going to have a multi-part talk in which we are going to discuss, first of all, getting started with working with the PDB. So if you don't have experience downloading proteins from the protein data bank, we're going to show you how to do that. Then we will tell you about how to view those coordinates in two of the most popular molecular visualization software options, PyMol and VMD. So we'll begin with our taking a survey of the PDB and how to do a search there. So the first thing we're going to look at is the actual PDB website. You can go to this PDB at www.rcsb.org. They have a lot of interesting information on their front page, including molecule of the month and some links to various biological structures. And I'll call your attention to the search bar right up here, which is going to be where we can go to actually get the coordinates. So the PDB is a repository of XYZ coordinates of molecules. This is the most important and the only major place where people put their coordinates when they solve structures. They are mostly crystal structures, but there are also additional structures besides that, such as NMR structures and much more recently cryo-EM or cryo-electron microscopy structures. And so this is atomic resolution data on what the molecules look like from the experiments. If you want to find something in the PDB, what you can do is you can go to this box right up here and you can type what information you're looking for. So you can use a keyword search, author search, or if you know the PDB ID of the molecule you want, you can go to it directly. So you just put that in there and press enter or go, and then you will be able to find your molecule. So this is an example of what a search will look like. You'll pull up a page here that has a home page for each of the molecules that met your search criteria, and then you can click on those to find out more about your molecule. You can additionally refine your search results using the pull downs down around here. So you see that we have these refinements on the left. So we may wish to say that, so we search for oseltamivir here, which is an antiviral drug. And so what we might want to do is we might want to see that in influenza A viruses, or maybe we're interested in influenza B viruses. You get the idea here. We can refine the search by clicking on those, and it will show you the more relevant structures for what it is that you're looking for. So one of today's molecules is going to be the 4W4A structure, the crystal structure of neuraminidase from the H3N8 influenza virus. And that so happens to be related to New England. And so I thought it would be an interesting one to take a look at. This is what we see on the homepage. The 4W4A, 4WA4 is going to be the PDB ID, so it's good to record what that is in case you ever need to go back and find your molecule again. You'll see that there are links to papers about the molecules, so that would be the major paper that this article refers to this structure. So you can go here. You can also see the classification of it. You can also get an idea for how old or new it is, which could be useful if you want to know if this structure is the latest version or not. Here, these are the deposition authors, which are oftentimes the same authors as the major paper. It tells you what organism it's from. This is the expression system, so you could have the sequence from influenza A virus, but you may express it in something else, like an E. coli expression vector, for example, could be a common thing that you will see. And this is going to report on how many mutations you have. And then finally, you can see that there are some links out to other databases, one of which is the structural biology knowledge base. And as you scroll down in your homepage, you may discover that for your molecule that there are even additional ones beyond that. You can also interactively preview the molecule right in the web browser. So for example, this is showing what that web browser looks like. So you just scroll down to this section, you see we have the 3D view tab clicked here. And so then you can actually rotate your molecule and so forth right in your browser to see what it looks like. So now that we've seen a little bit about the PDB and how you can learn about your molecules from reading the information on the PDB, let us talk about FASTA and PDB file formats. So a protein or another macromolecule in the PDB is going to have information available about it. One of the things that's available is its sequence. So the FASTA file format is what will have the sequence, and you can download this from the PDB by using the pull-down menus and picking FASTA. So the FASTA format includes a line with this little greater than sign, which basically is the marker for being a comment. By convention, this typically has some information about what's here. So because these are PDB FASTA formats, they're going to include the PDB ID and then some information here. And then we have the actual protein sequence, so all the letters that are involved in it are listed out here. If there are more than one chains, you would then see something that looks just like this, so you'll know that it's the start of the new chain or the next molecule, because there'll be another one of these greater than signs. So that's just basically how the format is parsed. This is an example of the PDB actual data file format. So what we have here is a file format that's used to report the XYZ coordinates of molecules. The first column will say typically either atom or heteroatom. So atoms are for the major atoms, and heteroatoms are usually for some associated molecules like co-crystallization agents, drugs, and that sort of thing. And then what we're going to have here is the atom index number. So the index is going to run from 1, and every atom has a unique index. The atom type is telling the type of the atom, which is not to be confused with the atom over here. So atom means just what you would see on the periodic table, but atom type will differentiate between the different ones. So for example, Ca stands for carbon alpha, the alpha carbon type, which has the tetrahedral configuration. And so that would be something to be important to differentiate. So within a particular residue, no two atoms can have the same atom, cannot have the same atom type. So this is basically, these are going to be unique within a residue, whereas the atom itself, the column over here being on the periodic table, of course you could have more than one carbon in the same residue. So that's what the difference between those are. Okay, this is going to be the 3-letter amino acid code. And so every amino acid has a single letter code and a 3-letter code, and the PDB file format uses the 3-letter code, and you can easily find what these are on the web or in a biochemistry or biology textbook. The next thing we have is the chain of the molecule, and so what that's going to do is all of the amino acids that are strung together from an N to a C terminal part that are all bonded together will be a single chain, and then if there's another chain, then you'll get a new chain letter designation. The next number is the residue number. Interestingly, we notice that this file begins with 81. So how could that happen? Why isn't it number 1? Well, that could be because not the entire molecule was able to be crystallized. So what could happen is that it may be known what the entire sequence of the protein is, but maybe a truncated version of it was actually solved. And so because we would like to be consistent with the numbering in the complete one, we may begin with a number besides 1. Next, we have the actual X, Y, and Z coordinates. So after all, what we're going to be doing is plotting the points for the atoms in an X, Y, Z coordinate system, and that's what these are for. The next number is always consistently 1 and really doesn't carry any information. The one after that is going to be the B factor, and that's going to be reporting on, depending on how you look at it, the error of how well the position is known or how much it's fluctuating in the structure itself. So a sort of an error message. And then we get the atom again, which we've already mentioned. So that's the contents of the PDB file. And so this is just going to be pointing out how you can download them, right? So you're going to click on this button here, right, to download the file, and then what you're going to do is you're going to pick which kind you want. So here we're picking the PDB file as opposed to, for example, the FASTA file. And so then we'll just select that, and then we say save file, and we can download that to the desktop. So then that brings us to our first visualization software. So we will take a look first at PyMol. So to get a an idea of what PyMol is like, first of all, you will need to download this. If we were on campus, this is available on all of the computers that are part of the Wesleyan Image, but you can also download this for free for academic users. So you can go to the pymol.org website and pick download now, and you will be able to download it for PCs and for Macs. Once you've done that and installed that on your computer, all you need to do to launch it is just double click the icon that installs on your desktop, and you will see this. So notice that we have a couple of different windows here. So we have the interactive interpreter up here. We have a series of buttons that are over here on the right. This is the main window where we're going to be actually seeing our molecule. And over here, we have some additional modes and the controllers that will be used for making movies and so forth. So suppose you want to load a molecule from your computer. You're going to do File, Open, and then navigate to your file. And then you'll be able to open that PDB file on your PyMol. If you encounter some problems, some of the common things that may happen is that you may have downloaded this from the PDB and it may be .txt, a text file format, and so it may not be immediately recognized. What you can do to preempt that problem is simply just change right here where it says the file format type. Change this to all files so that your file will then become visible, and if it is in fact a PDB file in terms of its contents, it should be able to be read by PyMol. Okay, a few tips. Yes, I just mentioned this. If you're having problems opening it because it's not called .pdb, use the all files. And if it's not automatically assigned, also you can use this trick in order to get into your file. So then once we load the molecule, we could also load the molecule directly from the PDB. So if you know your molecule's name, you can do it just like this. You can, at the prompt, okay, so you don't type the PyMol greater than here, that's your prompt right here. You're gonna type fetch and then 3DEQ. This is the PDB ID of the thing that I want to see. So you type that there and it will go to the PDB and it will download and display those coordinates for you, which is a shorthand if you are using a standard molecule from the PDB. So you can use your mouse to manipulate the molecule, and this should be fairly intuitive. I will mention that occasionally it may be mapped slightly different on your computer, but generally speaking, this is what it's going to be set up to do. Rotate the molecule is going to be left click on the mouse, zoom will be the right click, translate is the middle click, and change clicking planes will be rolling the mouse wheel, but do not click. If those things do not work on your computer, you can try some other combinations which involve using Shift and Control with your mouse buttons, or also your how do you call it, the trackpad on your laptop. Standard presets is very useful for orienting your molecule. We have reset, zoom, and orient. So if you move your molecule around too much and you get lost in your structure, you can use these presets to make it oriented back on your screen, and can also be a good way to get a good view of your molecule. In addition, we have clickable menus. A is for actions. So S is for show, H is for hide, and C is for color. So it's these right here. And so here we can select on these to do things to our molecule of interest. So a great way to very quickly get a molecule looking great is to do action preset publication, which will generate a publication quality image automatically. Basically what it's going to do is it's going to take your protein and show it in a sort of a cut down version that involves just the ribbon diagram. It's not showing the side chains of the protein, and it will show the ligands that are here, and they are being shown in stick, which is basically what it will do. This is a great way to get started. If you have residues of interest in, say, an active site of interest, you may want to go back into this and go ahead and add those, and we'll be showing you how to do it. But this could be a great way to get started. Ray tracing is a way that you can make your images output in a much higher format. So when you're looking at them in PyMol, they're going to be displayed quick and dirty so that it will rotate quickly and so forth. But you could use the ray tracing to make a view of your molecule that will be high resolution, that would be suitable for publication in a journal and or putting on your poster or putting into a presentation. So what you're going to do for this is use the ray command, and it takes the width of the image in pixels and auto adjust the height to maintain the aspect ratio of what it is you see on your screen. So that means 2400 pixels makes an 8-inch wide image, which I mentioned because that is a standard width for making figures for publication that are going to be 1 page wide. So if you're putting it into a single column in a publication, you would probably pick something that's half of that. You can use the PNG command to export the portable network graphics image. If you need to convert it to something else, you can then convert that using something like the Adobe Photoshop, or you can even use a PowerPoint to help you do your image conversions if you need to submit it to a journal in some other format. In addition to making still pictures, you can also make movies, and we have presets available to do that in PyMol. So here we are zooming in on that lower right-hand corner to see what those look like. So what you need to think of when you are making your PyMol movies is kind of like make this layout to see what you want your movie to do. PyMol is basically going to do the animation in between some snapshots that you give it. So it will basically morph between them. Okay, so you want to think about particular frames or views that you want to see. So what we're showing here is 1, 2, 3, 4 particular points of interest, and then PyMol is going to interpolate what happens in the interim, rotating it to match, to fit, or perhaps zooming in or out, or whatever it needs to do to get to where it is. So basically, we're going to have this movie plan. We're going to start with a zoomed out snapshot like you'd download from the PDB. Let's zoom in on a drug. Then we're going to stay zoomed in on a drug, so it'll feel like it's paused there, and then it will zoom back out again. Okay, so what we would do then is we're going to think about, well, how long do we want this movie to be? So this is going to be about 3 seconds. So at point 0, we will have 1 frame where it is zoomed out, and we could also have that same frame at 90 so that it will start and end at the same place. And then we'll have some different frame where it's zoomed in on the drug. So that gives us our movie plan, and we'll need that information to actually write our script. So what you do is then you're just going to load that into your script using those menus, and we will take you through that in a lot more detail when you're actually working your tutorial today. So next we're going to talk about rendering molecular features using the menus. So for example, maybe you didn't want to use the preset, maybe you wanted to do something in particular. So S, see how we have S down here. This is going to be for displaying the sequence. This is very useful for making selections. So what happens is it adds this bar up here, which is the sequence of your protein or molecule. And so you can in fact actually make selections. See how it's highlighted in blue here? That's the section that's highlighted down here. So you can select the molecule down here and it will show up in your bar and vice versa, which is really nice. Notice that we have some information also being shown over here. This is the different views that we have of that molecule. Next, we're going to do an example of using the ASHLC buttons to construct a view. So H, everything is for, all right, so these are those buttons that you can use on those pull-down menus in order to make a view where you're going to customize what it is you want to do. So these are the steps you can take in order to make a view that's seen over here. So if we do H, everything, right, that'll hide everything in S. Cartoon will show everything in cartoon. Display the active site catalytic residues. So these just happen to be the residues in the protein that are of interest for this molecule. So we can make a new selection using the slider to locate the residues by finding that number on the top and clicking on the letter. So how I showed you that when you use the S to show the sequence, you can then go to that number, and then you can just click on the 1-letter amino acid code that matches to these residues of interest. And next, what we're going to do is we're going to rename the newly created selection, which is then is going to appear as cella in the molecular list. And here we are going to rename that to active site, and then the active site residue can be manipulated independently because it's its own selection. So you can do that by going into the row with the cella, and you can do show sticks, so that'll be as sticks, and color the molecule by element. So C element, pick color scheme, right? So you can, this one looks like CPK, and then we can save the selection as active. So you're going to do A for action and then rename selection. And then you can go and type a new name for it, which we could call active. So another thing that PyMol really excels at is doing the superposition of molecules, that is taking one molecule and overlaying it on the other. You can see here that we have superimposed two molecules, and they can be seen to be right on top of each other, so that we can quickly see then which parts of the molecule are different. This can be done using pull-down menus and is fairly straightforward to do in PyMol. This can also be done in VMD. However, the difference is that in VMD, it requires more stringent criteria in order to do the superposition. That is, the number of atoms must be identical, whereas whereas PyMol is a little bit more forgiving, and so is what I would recommend you do your superposition to do. This is some instructions on how to do that, and you'll also be taken through this in the workshop. So I suggest that you work those tutorials if this is something of interest. What you would do is you load the first molecule, and then you load a second molecule that you want to superimpose, and then you do molecules from the PDB, loading fetch, right? So we learned how to do that to do this. And you can also do file open. Then you can do the alignment like this. You're going to go to your action menu, and then you're going to go to align, right? And then you're going to do to a molecule, and then we're going to do this to 4WA4, which is the PDB ID, which matches another molecule which is loaded in PyMol already. And then it will superimpose your molecules. So then in this part of the workshop, what you're going to learn about is becoming familiar with the PDB. So you'll do a PDB search, identify some molecules, and there'll be a couple of questions to get you familiar with looking around to see where that information is available. You'll also view the sequence of the molecule in the FASTA format and identify information about the molecular ligands, as well as practice with downloading a PDB file. And then in the section with PyMol, you're going to load molecules of interest and set up a quick visualization of them. You'll practice with rotating, zoom, and translating them. You'll change the representation of the molecule and practice by saving a publication quality image. You can also make movies using the preset animations that we previewed here. We will take you through step by step, actually all the commands to make the movies in the tutorial. Then you can superimpose the molecules and compute the root mean square deviation, which is a common number to compute in order to quantitate what the differences between two structures are. All right, well, we hope you enjoyed this part of the workshop. We hope you'll join us back to learn also about the second molecular visualization, which is VMD. Thanks so much and have a great day. We will see you next time.